Okay, so for our purposes, the notation we're going to use is, so we're going to let x of t be the position of some particle, right? Or it could be, say, the position of a car, like a road or something, but it's the position of something. T is time, right? So we're thinking of this position as a function of time, right? It's changing over time. And we're going to let v of t be the instantaneous velocity. Right, so this is just notation. Somehow velocity is related to position, right? Velocity, is kind of somehow how fast position is changing, right? Well, once we get to derivatives, we'll kind of give a precise definition, but right now we're going to try and kind of figure out a good approximation. Now, one thing that you probably learned in pre-calculus was average rate of change or average velocity or something like that, right? So average velocity. So what if I wanted to know, what is this particle's average velocity over a certain time interval? So over the time interval, let's say t1 through t2. So this is kind of a very quick review of what do we mean by average. Does anyone remember what the average velocity would be over a certain time interval? You may have also heard it as average rate of change. Does anyone remember how to figure that out? Not all pre-calculus classes actually do it, to be honest. Yeah, it's slope, right? It's some kind of slope. So in particular, if I look at the position at 2 points and I just look at the slope between of the line between those 2 points, right? So actually the formula that Reynold actually just wrote down. So this would just be delta x over delta t. So this would be, say, x of t2 minus x of t1 over t2 minus t1. So keep in mind, colloquially, we talk about average velocity kind of all the time, right? Especially when you want to kind of figure out, like if you're planning like a trip, like how long is it going to take you to get there? Okay, it's 100 miles away. If we're on the highway a little bit, okay, we'll go 50 miles an hour on average. So that means it'll take us 2 hours to get there, right? A lot of times when we're talking about planning trips, we talk about average velocity, right? So let's actually jump right into an example. Can anyone tell me, so that would be what average velocity is, right? I did a 100-mile trip over 2 hours. So on average, I traveled, so let's see, 100 miles over 2 hours. On average, that's 50 miles an hour. So that's average velocity. Can someone kind of describe very briefly, using this car analogy, what is instantaneous velocity? Because there is a big difference between average velocity and instantaneous velocity. So in this car analogy, what is the instantaneous velocity? How would you figure that out? So let's see. So Jacqueline said the speed at a certain point in a trip. Good. My velocity at a given time, the velocity at a c, right? The velocity of the car at a moment, right? So how do you actually figure that out in your car? Like when you're on the highway, how do you know what your instantaneous velocity is? Right? It's a very easy way. Your speedometer, right? So whatever your speedometer actually says, that is how fast you're going at that moment, right? Now, strictly speaking, the speedometer doesn't really measure instantaneous velocity, because how the speedometer actually has to do that, so different cars have different ways of measuring it, but the most basic way of doing this is to kind of have like an internal clock and kind of measure how fast the tires rotate in a certain time. And if you know the radius of the tire, then you can kind of estimate how far the car has traveled in that time, assuming the car is not skidding. Right? We know that when your car is skidding, sometimes the speedometer actually doesn't really work. And so what the car actually does, a lot of cars, they measure your average velocity, but over a super, super tiny time interval, like 0.1 seconds or something. So you get a very good estimate of your instantaneous velocity, but it's actually kind of not quite the instantaneous velocity. Okay, so let's look at this first example. So suppose we're actually given a formula for the particle, the position of a particle. So I'm not saying the speed of car is going as the instantaneous velocity. I'm just saying that the reading on your speedometer is technically an an approximation. Although you'd have to have pretty sensitive instruments for you to be able to kind of notice the difference. Yeah. So let's estimate the instantaneous velocity at t equals 2. Okay, so what we're going to do is we're going to actually estimate the instantaneous velocity using the average velocity, right? This is kind of just what I described to you how cars actually do it, right? Or maybe some old model cars. Right, I'm going to estimate the average velocity, or actually, I'm not going to estimate the average velocity. I'm going to calculate the average velocity over a certain time interval. So let's actually do that. So we can estimate the velocity at t equals 2 with the average velocity. Now we know that, so instantaneous velocity means a velocity at a specific time. Average velocity is taken over a time interval, right? So what time interval would you like to actually use? What time interval do you think would be useful for a good estimate for this particular velocity? Let's see, 1 to 3. 1 to 3. So it looks like you guys like to choose kind of central intervals, right? Where the point t equals 2 is kind of in the center. Now that does work. That's perfectly fine. Except that's technically not how we do it in calculus. It turns out that using an interval where the number we're interested in, t equals 2, is in the center, is actually not a good way to do derivatives, it turns out. So we're actually going to use an interval where t equals 2 is actually either at the left endpoint or the right endpoint. So for now, I'm going to choose the interval 2 to 3. But it turns out making 2 in the center, why that's actually a bad idea. It turns out that that's actually a pretty advanced and subtle issue. And there'll probably be an advanced homework question or example like that later on to show you why we don't want to do symmetric intervals. Okay, so let's do an average velocity over 2 to 3. Okay, so this is basically just a calculator question, right? So let's look at. Well, I just realized I can do fancy dashed and dotted lines. And I got very excited. So. Why don't we just plug into the original equation? Well, the problem is this equation doesn't give you velocity, Miriam. This gives you position, right? Okay, so let's look at v bar. Okay, so let's just look at delta x over delta t. So that means I want the position at, so actually I lied to you. We're not going to do 2 to 3. We're going to do 2 to 2.1. That was what I originally had in my notes. Although 2 to 3 is fine. But let's just start with 2 to 2.1. Okay, so x of 2.1 minus x of 2, right? The change in the position over the change in time. How do I get x of 2.1 and x of 2? Well, that's the original function, right? So 16 times 2.1 squared minus 16 times 2 squared all over 2.1 minus 2. We get out our calculator and we get 65.6, right? Nice and easy. Okay, so apparently this particle is traveling at approximately a velocity of 65.6 at t equals 2. I didn't give any units. Let's just say meters per second, just for sake of definiteness. Let's say x is measured in meters and t is measured in seconds. Okay, so I've estimated that the particle on average, or about moves at 65.6 meters per second at t equals 2. Now, obviously that's only an estimate. How do I get a better estimate? I mean, I know that that's an estimate, right? I know that I know I could probably get an even better estimate. So how do I get a better estimate than 65.6? Well, take the derivative of the function. Well, you're getting ahead of us because actually this is the motivation for derivatives. We need to define limits first before we define derivatives. And that's actually the point of today's lecture. But you are right that velocity will come from the derivative position. But let's try to go back a little bit and try to motivate this first. Let's see. So Artsy said smaller time interval. Maya Nicole says you can use more precise numbers like 2.01, and Nishika make the interval more specific, right? So let's use precise language. So we don't mean that the interval is specific. We don't mean the numbers are more precise. We actually just mean that the interval is what? The interval is a smaller length, right? That's what we're really getting at, right? I know you all mean that, but let's try to use precise language. All right, so let's use a smaller interval. So we get a better estimate by using a smaller interval. Okay, so let's kind of write down a whole chart. Okay, so I'm going to note what is the interval here. All right, what is the delta t? That's what I want to note also. And then what is the v bar for that interval? Okay, so we've already done 2 to 2.1. Now let's do, say, 2 to 2.01. We can do 2 to 2.001, right? We can go even smaller than that. And the other thing we didn't talk about is we don't need 2 to be at the left endpoint, right? I just said we should not choose 2 to be in the center of the interval. So we can also do, say, 1.9 to 2, 1.99 to 2, right? We can come kind of from the other way. Okay, so what is the time interval in each of these cases? So that's 0.1, 0.01, 0.001. This is an interval 1.01, 0.001. Okay, and then you calculate v bar, right? X of t1, or x of t2 minus x of t1 over t2 minus t1. This is just a bunch of calculator stuff, right? So we get here, this was 65.6, right? And then we get 64.16, 64.016. Then here, what do we got? Does I have this somewhere else? 62.4, 63.84, 63.984. Okay. So that's all done by a calculator, right? So I've done it for you. Now here's the question. What is the relationship between, whoops, what is the relationship between this column of numbers and the second column of numbers? Now I'm not necessarily looking for a formula. Like I don't want you to say, oh, if delta t is this, then v bar is this. I'm not looking for a formula. I'm looking more for qualitative descriptions. So let's see. So what have some people said? So Adam says number of figures after decimal point. So can we be more precise? What do you mean by number of figures after decimal point? The smaller the interval is. Do you actually know that these are more precise estimates? Do you actually know that they're getting more precise? Is that true? They could just be going off the rails. They could just be giving you numbers that are nowhere near the actual velocity. Camellia says the smaller delta t, the closer you get to the actual instantaneous velocity. So that's kind of, I think that's kind of the same comment, right? How do you know you're actually getting closer to the actual instantaneous velocity? Aya says chance of time or change of time in the velocity over time. Jacqueline says uncertainty is in the same place. I'm not sure what you mean by uncertainty is the same place. Jordan says the smaller the interval, the closer it gets to zero. I don't know what you mean by it gets to zero. I don't know what it means, and I don't know what's getting to zero. Miriam says as the number on the left, so delta t, gets smaller, the closer the number on the right gets to what? I think you wanted to say a little bit more than that. Josh says they both approach a specific number. Okay, so it looks like everyone is kind of saying sort of the same thing. let's try to get this kind of more precise. So I would say the best qualitative description of what's actually going on, and this is kind of a combination of what a few people have said. So as delta t gets smaller, so as delta t gets smaller, in other words, closer to 0, what happens to V bar in response? V bar, so a few of you said, oh, V bar becomes a better estimate of the velocity. We don't actually know that just from this. It is true, don't get me wrong, you are correct that it does become a better estimate, but you don't actually know that just from this chart. So the best I can say is that V bar does what? V bar gets closer to what? 64, right? I think that's about all we can really say. We don't actually know yet that 64 really is the true velocity. It is the true instantaneous velocity, but we can't actually say that in our statement. Okay, now this is where the original problem, remember, was actually estimate the instantaneous velocity. Now this is where kind of the leap of faith comes in. Okay, we see that as delta t gets smaller, so as I shrink the time interval, the average velocity gets closer to 64. So like a lot of you have said, it's reasonable to expect the velocity actually is 64. So that's what we say. So we estimate that v of 2, right, the velocity at t equals 2 is 64. Again, this is not a proof, but this kind of shows us it's probably a reasonable estimate if we're